Hi, everybody, and welcome to a very special Science Museum online event. So wherever you are in the world, thank you for joining us. I should start by letting you know that we're with you online tonight, but the Science Museum and our sister museums across the world, across the UK, are open and ready to welcome you all. I'm really excited to be chairing what I'm sure will be a fascinating exploration of the nebulae that give birth to the stuff we're all made of, stars. So tonight we are discussing Cosmic Clouds 3D, the new book published today, created by Brian May, David Eicher, and J.P. Metsävainio. Now, if you're watching live, we have a very limited number of copies of the book signed by Brian. You can grab a copy of those by following the link in the description below. If you're watching this later, not live, we might still have some copies, maybe not, but follow the link to see if you can get yourself a copy while stocks last. So we're going to see three presentations this evening from the three creators of Cosmic Clouds 3D. Some absolutely glorious cosmic imagery is about to come your way, and I'll be chatting with them later in the evening. You'll also have a chance to ask your own questions, so fire them in via the chat box. But first of all, some introductions. So tonight's speakers are David Eicher, creator of 25 books on science and history, known to many of you as the editor of Astronomy Magazine. J.P. Metsävainio, visual artist, astrophotographer, whose incredible 3D images bring the book to life, and the creative director of Cosmic Clouds 3D, who I'm sure needs no introduction, but I'll do it anyway. Legendary guitarist for Queen and astrophysicist, whose passion for stereoscopic imagery has led not just to Cosmic Clouds that we're talking about tonight, but also Mission Moon 3D, which we discussed last year at the Science Museum with astronomer Royal Martin Rees. So here to talk to you about the creation of the book is Dr. Brian May.
Oh, I'm very overexcited and very happy to be here. Thank you, Ali, for that lovely introduction. Thank you to the Science Museum for hosting this event. Very grateful to you. And thank you to my colleagues who are going to make all this happen. Thank you all for being there. I hope some of you at least have got your viewers ready, because we're going to do some of this in 3D. Some of you may have your OWL VR kits ready with your phone like this, and this is the best way to watch it, like this. Okay, and we hope that this is going to work. But there are other ways. If you're watching it on your laptop and you're free viewing, what you can do, seeing as you're on YouTube, you can make your window smaller until it's easy to free view if it's a problem because generally if it's full-size screen, it's a bit difficult to fuse. But hopefully you got your viewers ready. You don't have to see it in 3D. Obviously, you can watch this in 2D all the way along the line if you like, and everything will be fine. So relax. Why is this important? Why is this book important? Well, I'm going to tell you, but what I'd like to do is start a bit closer to home and explain why we have two eyes and why it's so important to us, and how difficult it was to make a book about nebulae, which are billions of miles away, in 3D. So if you're ready, I'm going to share my screen, and you won't see me anymore like this. You'll just see me in a little corner of your screen. So what I do now is I share my screen, and we will go to 3D. Are you ready? Yeah, I can hear you ready. Now I have to find this and open it, wherever it is. And I can't see it. Where is it? There it is. And I press play. I press play right here. And there you should have it. Now, if you're just watching normally, you can see two images side by side with a bit of a gap in the middle, a black gap in the middle. If you've got your viewers ready, just relax your eyes and get used to watching in 3D. This is our little ad. I'm going to steam into what stereoscopy is and why we care about it. So if you're ready for the first slide, this is it. I love this one. This is by my dear friend Carleen Phillips. I love it because you can't see what the hell it is in 2D, which is the way you're looking at it now. Luckily, we have two eyes. We evolved with two eyes instead of one. Why? Because it gives us a much better perception of what's going on around us. This is the left eye view. This is the right eye view. And if we let the miracle of stereopsis happen now, this is the view you get. So I'm hearing this, ooh, coming back now. I'm imagining it in my head. But this is what turns us on as stereoscopists. You know, you get so much clearer an idea of what's around you with the stereoscopic vision. You can now see that this is a leaf with some hailstones on it, and you never would have figured it out looking at this. So this is why we're interested in making 3D books. We've been doing it for quite a while, London Stereoscopic Company, but this is the furthest out into the universe we've ever tried to go. Let me explain to you why that's difficult. Another example close to home. This is a very well-known site, a flower around you. Doesn't look that great flat. It's got its color, it's got its shape. You kind of know what it is. But again, you've got a left eye and a right eye picture. If you fuse the two in stereopsis, it looks a lot better. And if you're seriously wanting to study things, you can tell you get so much more information in 3D. Now, this all happens because our two eyes are about 2.5 inches apart. So we get these two views, and the two views have little tiny parallax differences between them. It's all about having the baseline between these two eyes, 2.5 inches here. If we go outside, I'm just going to say this is the man who invented it. Charles Wheatstone, 1832. Nobody figured it out before he did, not even Leonardo da Vinci, but it's thanks to Charles Wheatstone that we understand and we have 3D images and we have 3D films now. Thank you, Charles. Okay, we're going to go outside now. This is flat. This is what you would see with one eye. And with your two eyes, it's like this. Now, it's not bad, but you can see the tree just about stands out from the background, but you can't really see what's going on in the bushes behind. You don't get a real feel for the depth of this picture, do you? So what do? We increase our baseline. We're going to imagine now that our eyes are a couple of feet apart instead of a couple of inches, and this is what we get. So now it's a lot clearer what's going on in what they call the Z-plane, the depth plane. So what we're looking for in every case is getting a baseline long enough to see things in true 3 dimensions. So moving onwards and outwards, what can we do with the solar system bodies? They're a long way away. The moon's about 1/4 of a million miles away. So we would need a baseline several 100,000 miles long in order to see this in 3D. Unfortunately, even the Earth isn't big enough to do that instantaneously, but the moon keeps its same face towards us, right? Well, not quite. The moon actually wobbles because it's in an elliptical orbit. So again, if you wait your time, you will get a left view and a right view, and you put them together, and you get a nice stereoscopic, in-depth view of a round-looking moon. I love it when it's not full moon because you get this beautiful what they call the terminator, the line between dark and light, where you can see actual craters in 3D as well. So I enjoy that. This is solar system astronomy in 3D. What do we do with Mars? It's a bit further away. Well, Mars, in common with most astronomical objects, rotates. So if you wait your time, you can get a stereo image as well. It wasn't actually done this way. In this case, this was because there was a probe that went to Mars and it moved around the planet. So we were able to get our 3D image like that. And you can see Olympus Mons there in the middle, 3 times the height of Everest. And you can actually see it in 3D in this picture. I've been lucky to be involved in some of the NASA and ESA missions, and this is one of them. This is Rosetta's comet. And I was able to put some 3D pictures together, and this is one of them. Again, I'm kind of blowing the trumpet of stereoscopy because you can't really tell what shape the comet is, can you? This is a comet, a very sooty and dark object, but it looks kind of amorphous here. Again, a left view and a right view because the probe was moving around the comet. Put them together, and now you can really see what shape this is. It's very obvious. So it's nice to use stereoscopy to make things very instinctive, and astronomers, I find, very much enjoy this. You can talk about maths for ages, you can draw graphs of things, but if you actually see it in 3D, you get an instinctive understanding. It's almost like being there. Moving on, I was very lucky to have been in the New Horizons control room when the images came in, the very first images that mankind has ever got, close-up of the planet Pluto. The first image was this one, which is the last before the flyby. This was the flyby picture, and a couple of minutes after that, I was able to put the two together and make this image, which I will never forget. That was a moment for me, seeing Pluto in 3D, and of course the whole control room was full of joy. Thanks to Alan Stern for making that possible for me. Alan Stern's the PI of New Horizons mission to Pluto. I'm going to stay with New Horizons for a moment because this is another experiment, which is a lot of fun, really. Talking about baselines, remember, Suppose we wanted to see the nearest stars in 3D. Nearest star is a long way away. It's a few light years away. So how can we possibly get a baseline that would be long enough to see that in 3D? Well, the New Horizons probe was about 1 billion miles away from us when it took this picture. This is the picture, this is the view from the New Horizons probe way out in the Kuiper Belt. And this is a picture which was taken by an amateur astronomer on the Earth at the same time. So you have a baseline of 1 billion miles, put them together, and indeed you can now see Proxima Centauri, that little bright blob upper center, in 3D leaping out at you, because it actually does stand out in 3D. Now that's a technique that's never been used before. That was a first, getting parallax from a space probe. Now, this is all very well, but what happens if you want to take a picture of a nebula, as we wanted to do for this book? These things are many light years away, not just a few, but hundreds or thousands of light years away. So how can you possibly get your eyes far enough apart to take a 3D picture? Well, you can't. And that's where J.P. Metsävainio came in. Metsävainio, I should say. The genius of J.P. was to take his own pictures for a start, and his pictures actually rival the Hubble telescope in their detail and splendor. But then he got all the scientific evidence that he could get together, all the astronomical data, and he made one of the images, the image that you would see if you were standing 1 billion miles to the right, actually several billion miles to the right. So these are pictures which are made out of current astronomical knowledge and the skill, the science and the art of JP. Here's his left picture, which is the one he took. This is the right picture, which he generated using the astronomical data. And this is what he came up with. So suddenly, it's actually quite a shock to see that this thing isn't a smoke ring after all. It's a tunnel, and the tunnel just happens to be pointing towards us. We're looking down it towards that tiny little star in the middle, which is the cause of the whole thing. This is a star that's exploded, as our sun will do, but we won't be around to see it, luckily. So this is the genius, and this is the only thing I did for this is put these two guys together. I have David J.Eicher, one of the foremost authorities on nebulae in the world, and J.P. Metsävainio put together, and the two of them make the first ever book on nebulae in 3D in the universe. I'm just going to end with this one. This is one of Metsävainio's beautiful shots. I think you'll agree, it's just exquisite. And again, you'd have no appreciation of it if it weren't for the 3D, not in the same way anyway. This is the image that I saw that fired me up to start this project. I saw it on his website and I used it in one of my talks at Starmus. And recently, I think you guys have seen it because that little clip that I made is up there, the Horizons clip, which is on YouTube. So that's it. Now, I'm going to sign off in 3D. Close your eyes for a second. And hopefully, if I close this up, you will see me again. Just in time for me to hand over. I'd like to hand over now to the genius who has written the text of our beautiful book. And he's in Wisconsin. Over to David J.Eicher in Wisconsin. Go. And I'll see you later.
Thank you, Brian. And what I'll do is attempt to share my screen here as well. And what I'm going to do is, can you see that okay now?
Yes.
Fantastic. Well, we've got a galaxy. So I'm going to talk a little bit about some of JP's magnificent images, and he'll tell you a little bit more about how he created these incredible visualizations that are really scientifically accurate. But first of all, I think we came out with this book at the right time because we're in a golden age of discovery in astronomy, of understanding these objects out in the universe in a very special, detailed way. It was only a century ago when we called this object, everyone called this object the Andromeda Nebula. But we now know that this is the Andromeda Galaxy. It's a huge system of stars. Stars, gas and dust, organize themselves into galaxies in the universe. We're in a galaxy ourselves, the Milky Way, that is similar to this Andromeda Galaxy. They're about 100,000 light years across, the disks of these big systems of stars. A light year is the distance light travels in a year. Of course, it's about 6 trillion miles. And what we know is that our galaxy is full of stars. It has about 400 billion stars, the Milky Way, give or take. And of course, you can see it as a beautiful band of light throughout our sky when you head outside away from cities. Well, we can't see the Milky Way galaxy from the outside, of course. That makes it tough to understand the structure of our galaxy. But just a decade and a half ago, we found out that our galaxy was a barred spiral, not just a simple spiral with spiral arms, but has a bar through its center, somewhat similar to M83 in Hydra. That's the galaxy shown here. So if we could see our galaxy from the outside, it would look relatively similar to this object, which is in the southern hemisphere sky. Well, the galaxy, as I said, is full of stars. Many stars are in clusters, not like our sun, which is now solitary, making its way around the galaxy over and over and over. Some stars are old stars that congregate into big clusters called globular star clusters, named so because they're globe-shaped. These are old stars that are on the periphery, well out away from the disk of our galaxy, that formed very, very early on. They're a good percentage of the age of the whole universe. But there are also other clusters of stars that are called open clusters of stars. And these are within the disk of our Milky Way galaxy and other galaxies. And these are young stars. And a lot of them are massive white and blue stars that are young. They've just turned on. Of course, stars are nuclear fusion reactors that convert their elements into heavier elements. And that's how they generate this heat and light and wonderful warmth and sunshine that makes us be able to be alive on a planet orbiting one. So this is the Pleiades star cluster in the constellation Taurus, a familiar winter constellation, and it's about 445 light years away. And it shows the kind of young environment of stars forming out of gas and dust, some of the dust still surrounding these young, hot stars. Well, then we go on to other examples of these kinds of cosmic clouds that we find scattered throughout our Milky Way. And most of these that we're looking at are within our galaxy. Of course, there are billions of other galaxies in the universe. This is called the Trifid Nebula from the southern sky, M20, that's in the constellation Sagittarius. And it shows us a couple of different types of cosmic cloud, if you will. The reddish glowing pink light here is a so-called emission nebula. And this is a very common type of these cosmic clouds. They're forming new stars. Of course, the universe is expanding over time as a whole, but it's also at a smaller scale engaged in the greatest cosmic recycling program that ever has been known. So old stars blast their gas and dust away, and gravity eventually will bring them back together to form new stars. And that's what's happening in the Trifid Nebula here in the pink area. And the bluish light that you see above it there is simply dust that is reflecting bright starlight back to us, to our line of sight. The pinkish emission nebula in this object is actually glowing of its own light, because the hot stars within it, you can see them in the center of this nebula, are exciting the gas into glowing like a fluorescent bulb. You can also see little veins of dark nebulosity here as well, and that's simply dust that is blocking the light from beyond. So there are multiple types of these cosmic clouds. This is the Crescent Nebula, and another one of JP's incredible images here. And you can see a bright star within this nebula. This is a young hot star that has been stripped of its outer atmosphere. It's a so-called Wolf-Rayet star, after two astronomers who discovered this type of object. And it is an incredibly intense hot star that is lighting up this cosmic bubble of gas around it so that it's glowing. This is in Cygnus, and it's a beautiful example of an unusual type of nebula. Well, I mentioned dark nebula. We saw some in the Trifid there, but everyone's favorite dark nebula in the universe, I think, has got to be the Horsehead, the so-called Horsehead Nebula, which I hope you can see in 3 dimensions here, really truly does resemble an equine shape. It's informally called the horsey in the astronomy lingo here. And it's visible, of course, because this strip of reddish nebulosity is behind it, and we get to see that dust. The densities of these areas of gas and dust of these cosmic clouds are very, very low. But we see them because they're very, very large areas of either light or dark. I'll get to what's happened. Brian showed the ring nebula. I'll show it, I think, again in a moment here, and we'll talk about seeing our future. But this is what happens in the late stage of a very massive star here. This is the Veil Nebula, again in Cygnus. And when a massive star, about 8 times the mass of our sun or more, runs out of material to fuse in its reactor, it explodes violently in what's called a supernova, an exploding star. And this is the supernova remnant, the debris from a star that exploded about 10,000 years ago. And you can see this shell shape of material in the veil. So these nebulae show us often the origin of stars, and they show us the evolution of how stars age. They also show us how stars die, because just as people, stars live and have a finite lifetime and they expire. The very bright, massive, energetic stars have shorter lifetimes, like this one, and the meek, faint, very dim and small stars live for very, very long periods of time. Our sun is in the middle of that spectrum. So this again is a J.P. shot of the Ring Nebula in Lyra, one of the most beautiful planetary nebulae. Brian explained that seeing these objects in 3 dimensions really allows us to see the shapes, not just sort of a static, flat picture, but the fact that this is a tube, it's a tunnel, we're looking down. The star in the middle of this Ring Nebula is the sun-like star of about the sun's mass that has run out of fuel to generate energy, and it produces what's called a planetary nebula, a sun-like star at the end of its life, so named by our friend William Herschel, because in the late 18th century, looking at these in a telescope, he thought they looked like the disks of planets. But this is what will happen to our solar system about 6 billion years from now. It will puff off layers of material from our sun, first at low speeds and then at high speed. And the shock front of that gas running into the other gas will light this thing up, and it'll be visible to other people or beings in other parts of the galaxy for about 50,000 years. So let me just conclude before I hand it off to JP to talk more about his technique and how he produces these truly amazing portraits. A little bit of the past, present, and future. We know that the atoms in all of our bodies were created in stars. Carl Sagan used to like to say that we're made of star stuff. Joni Mitchell also famously wrote about that as well, of course. This is the Rosette Nebula in Monoceros, and it's a stellar birthplace again. Again, it shows you a young star cluster in the middle of this object that's being born out of the gas that is compressing down by gravity, making a new generation of stars. So we're seeing what we had 4.6 billion years ago. When our sun formed, it was in a cluster like this. That cluster dispersed as it orbited the galaxies. Its sister stars moved away, and eventually will end up with that planetary nebula shape like the Ring Nebula. So we see in a unique way, for the first time in JP's images here, a view of our past, our present, and our future in the cosmos. JP, with that, I will hand it off to you.
Okay, thank you, Brian, and thank you, David. That was beautiful. I'm a visual artist and an astrophotographer, and I have been shooting these pale objects about over 20 years, and I always have seen them three-dimensionally in my head. Over time, I realized we might have enough actual information, scientific information, to build a kind of realistic model of nebula itself. But since celestial distances are so vast, it's not possible to take traditional stereo image pair for a 3D view. How accurate my 3D conversions are, depending how much I have had correct information and how well I have implemented it. The final 3D image, however, is always a simulation of reality based on known scientific facts, deduction, and of course, artistic freedom. I will use my photo of NCC 281, the Bachmann Nebula, to explain how I have done my 3D conversions. Just a second. Okay, here we go. This emission nebula locates in Cassiopeia at distance of about 9,500 light years. And I start my 3D conversion process always from the stars. Usually there is a star cluster responsible for ionizing the elements in the nebula. It's here, if you see my cursor, it's here in the middle. This cluster has to be very close to the nebula center itself. The apparent brightness of the star can be used as a distant indicator. Bright means closer. By using a known distance of the nebula itself, I can locate then a correct percentage of stars front and behind a nebula. The actual nebula structure then, how it's done, it's next step in my process. Emission nebulae are not lit by the starlight. They are usually way too large for that. And the stellar radiation ionizes the elements in the gas, so the nebula itself is emitting light, glowing light, typical to each element. The principle is very much the same as in fluorescent tube. The thickness of the nebula can be estimated from its brightness, since the whole volume of gas is glowing. Brighter means thicker. The local stellar wind from the star cluster in the center of the nebula creates a cavity around it by blowing away the gas and dust around the cluster. The collapsing gas then resists the stellar wind and produce a pillar-like formation. I mark them here in the white lines, as you can see. And they have to point to a star cluster due to solar wind or radiation pressure. Then the ionized oxygen, which glows here at the bluish green, needs a lot of energy to ionize, so it has to be very close to the star cluster itself. Many other small indicators can be found by carefully studying the image. For example, if there is a dark nebula in the image, it must be located at front of the emission one, otherwise we can't see it. Now I can build a skeleton model of the nebula. Then the artistic part is mixed with scientific and logical elements, and rest is very much like cosmic scale sculpting. Here is an animated version of this Bachmann nebula. And you don't need any 3D glasses to see this. This is not stereo, but this is a 3D animation. By the way, every single pixel in this animated nebula is from the original 2D picture. And you can see how the star cluster is located in empty space inside the nebula itself. The next sample is from one of my favorite objects, the Bubble Nebula in Cassiopeia. Its distance is about 11 1,000 light years. And the bubble itself has a diameter about 5 light years. And the bright star here is responsible of this shock front. And this star is actually a Wolf-Rayet star. And you can see its location in this animation. So this is volume. I want, with my animations, with my 3D models, I want to show that those flat-looking objects in a picture are actually three-dimensional, floating in three-dimensional space. The last sample is also my favorite type of object, the supernova remained. This remained located in Cygnus at distance of about 2,400 light years, and it's called the Whale Nebula. Since the supernova remained is a result of massive explosion, it has to be more or less spherical, as you can see in this animation. All the stereo images in a book are made from models like this. And you can actually dive deep in the space by carefully studying them. And because they are printed in a book, you have a lot of time to concentrate and see all the details. Okay, and I'm going to be back in a second. Okay, thank you all.
We're all applauding JP. Amazing.
Oh, thank you.
Back to you, Ali, yeah?
Thank you, everyone. That was fantastic. So that's given you something of a taste of this wonderful book, which you should be able to get from the Science Museum store. So keep an eye on the box there for the link to purchasing that in the Science Museum store. Thank you, all three of you. I'd like to start with Brian and David to tell us a little bit more about your relationship, because this isn't the first time you've worked together, is it?
No, we're old friends now. We've done a lot of very interesting, geeky scientific things together. One of my favorites was visiting the Arizona meteor crater. We did partly for fun and partly for business, I guess, or for collecting data, if you like. But it's been great fun. Every time David speaks, I learn. That's the way I look at it. He has an amazing broad view of astronomy, which is very rare these days because everybody's specialist these days. And the days of Patrick Moore, the man who knew just about everything, you say, what's Pluto like? He would say, well, if I walk down here, you'd feel like he knew his way around all the planets and everything. So those astronomers are very rare these days. And David is, I'm going to say, the last of a great breed, but hopefully the breed will carry on. But he's a very broad specialist. As you probably know, he's the supervising editor of Astronomy Magazine. So he gets to see everything that comes through. All the latest stuff goes through David. And I love to spend time with him when I get time.
Well, thank you, Brian. Yeah, we've had a lot of fun, a lot of adventures together. And we sort of, got to know each other, I guess, a decade or so ago and have spent time collaborating at Starmus with our pal Garrick. And that's led to these adventures with the books. Great fun.
Brilliant. I'm very proud of this book, I must say. I think it's a great product of our friendship. And we have a new friend in JP.
Yeah.
Definitely. And so, David, as Brian said there, you're a broad astronomer with a broad range of interests. So why nebulae in particular? What was the particular fascination for creating them for this book?
Well, I grew up the son of a professor of organic chemistry. So I was, as a toddler, hopping around an organic chem lab, but you never really want to do exactly what your dad did. So I was very drawn to science, but made the mistake when I was 14 of going to a star party and I saw Saturn and I was electrified. And long story short, the astronomy club got me to start writing about deep sky objects, and I started a little publication of my own. So galaxies, clusters, and nebulae have been very close to my heart for 40 years now, writing about them and observing them. And so, we did the moon book and had great adventures with that, but I thought it would be so much fun if we could do something that took us out into deeper space.
No, and absolutely fun it has been. And on that note, so some questions are coming in from the audience. We've got some questions from Mary Faragiu and Ismail Alcazar. So they would like to ask all three of you, what's your favorite nebula and what's your favorite image in the book? Now, those might be the same answer to those questions, but just in case they're not. So JP, do you have a particular favorite or a particular favorite of your images?
Yeah, I do. My all-time favorite are generally supernova remains, which are amazing because they are part of our history. We are from supernovas, so all the iron in our blood is from supernovas. So they are deeper meaning than just beautiful pictures. And as seeing them as 3D is to me, it's wonderful.
Thank you. And Brian, any particular favorites?
Oh, I think I'd have to say the Ring Nebula, because I was actually shocked. I grew up with pictures of the Ring Nebula, and I thought it looked like a smoke ring. And I thought, that's interesting, isn't it? And I think seeing JP's amazing creation was the first time I let go of that illusion, because it's not a ring at all. It's not a torus. It's a tunnel, and it really brings out what happens in an explosion of a star. It's not isotropic. Not everything doesn't go out in the same measure in all different directions. You get little tunnels and spikes and whatever, and we happen to be looking down a tunnel at the culprit, the star that's exploded there. And I found that absolutely riveting and eye-opening, and I thought, this is the way to go. We don't want to be looking at astronomical images in flat space. We want to be looking at them in three-dimensional space. So that kind of hooked me. Yeah, the Ring Nebula for me.
David, any advance on the Ring Nebula?
I'd have to say the Orion Nebula, because it's the first nebula that I observed a lot when I was very young. It's the first thing I took at my own astro photos of. But if we get to say favorite image too, then I would say the Carina Nebula, because when you're in the southern hemisphere and you see the Orion Nebula in the evening sky and you think of how fantastic and bright it is, and you look over in the same sky and see the Carina Nebula is 4 times bigger and 3 times brighter, the Carina Nebula has something.
And I'm sure all of you in the audience will have your favorites. I think in the book, my favorite is the Bubble Nebula one. I think because it's not one I'd see. You sometimes see some of these other nebula images quite often in the press, but the Bubble Nebula I hadn't seen before, and it's an extraordinary image. On the question of the imagery, we've got a question from Phil Parry. So are these extraordinary colors that we've seen in the images and in the animations, are they actual or are they manipulated in some way?
Every single color in my pictures is shot from the sky, exposed from the sky. But there's a different ways to combine those color channels, because generally astro cameras are black and white or grayscale cameras. So making color picture with them is like like 100 years ago, you made a color picture. You took a picture with green, blue, and red filter, and you combine them. So those pictures which look more like golden blue pictures are so-called Hubble palette. So the elements, the light from the different elements is combined so that they are balanced, so you can see different elements. But if you combine them different way, they are mostly red. There are some red pictures and some Hubble palette pictures in the book. And the red is one what you might see if you are able to see colors. So, but objects are so dim, you don't see colors even with a huge telescope. But they are not imagination. They are shot from the sky anyway. Thank you.
No, it's incredible to know that we're actually seeing what JP is capturing. Another question on the techniques of the images. This one's for Brian from Italia Simone. Brian, you mentioned that the images can be converted into stereoscopic imagery based on the knowledge we currently have. Does that mean it could actually be a completely different shape?
Well, JP's told me that as he gets more and more information, he does update his images. Yeah, so I think that's true. Yeah, you can evolve the images depending on how much knowledge you actually have. In most cases, I think JP's probably nailed it right now. But yes, the more information you have, the more you can put into your stereoscopic rendition. Yeah.
Well, there'll be future editions of the book. We'll be able to update it as we go along.
Yeah.
So David, can I ask, in terms of, you talked a little bit about the sun and the future of the sun. So what is the future for the sun, for our local star? What happens to the solar system as the sun moves through its life cycle?
Our sun is about halfway through its normal life, and that is as a so-called main sequence star, as a normal nuclear engine going along. It's 4.6 billion years old. And when it is about 10 and a fraction billion years old, it will go into a slightly different, more unstable future and start to burn heavier elements. And then it will eventually, about 6.5 billion years from now, undergo what's called the helium flash and become a planetary nebula. More, we don't know exactly what shape it will be, whether it'll be a ring nebula or like another shape of planetary nebula, but it will become a planetary and be a glowing disk of gas as it disperses its material and leaves a white dwarf star in its center, a very dense stellar remnant in its center. However, the prognosis, if we want to be all cheery in the middle of a week, for life on Earth is not to sit around and watch that happen, because the sun is also a variable star and it's increasing its radiation output over time slightly. So about 1 billion years, give or take from now, it'll be so hot. This is independent of global warming. This is the sun. It'll boil the oceans off of Earth, and that'll essentially be the end of life on Earth. So if any survivors of us see our sun as a planetary nebula, it'll be from somewhere else.
And on that note, obviously we won't be around when that happens, but if there is no future for a human race on Earth, do you think it's imperative we should try to leave the planet? Do you think it's likely that we can? I'll throw that out to all three of you.
Well, I have a pretty dim view of humanity, really. I do have this feeling. I love exploration, of course. I love the pursuit of knowledge. But it kind of worries me that if we go out into space and colonize other planets, that we'll make as much mess of them as we have of our own planet. It seems like we should learn to treat the planet and the life that's on it with respect before we have the right to go out and colonize someplace else.
And I would also add that unlike our love and wishes for science fiction films, moving a civilization outside of the solar system to another star and so on, we don't have enough time to talk about why, really, but that's a hell of a trick. It's the cosmic distance scale, even to the nearest stars around us. We saw with Brian with the shot of Proxima Centauri. It's unbelievably vast, the distances just to the nearest stars around us. So the energy required to physically travel even those distances just to the nearest stars is almost incomprehensible. So it's a tough challenge, because technology is going to change, the physics is not going to change.
Okay, not very hopeful there. Any more hope from you, JP?
I do like to stay here as long as possible, personally. But in some point, as a human race, we have to go. And I'm positive that I don't see the future as a dark. I see it's bright, and I'm optimistic. But I like to stay here personally, as long as I like to live in Earth.
Let me can I make one closing? 1 billion years is a long time between friends. That's nothing to be upset about. I think that we only have 1 billion years left.
But actually, I think you and Brian have talked about, also we should be looking at our own planet and how we treat our own planet. Last week we had an event with Joe Marchant and Martin Rees, and some of that was concerning the psychological benefits of stargazing and the feeling of awe that it can inspire in us. And David, you showed the images early on of, if we could see our own galaxy and see that we're just on a one arm of this galaxy. Do you think stargazing is important to give us a perspective of our place in the universe and maybe to be better custodians of our own planet? And again, I'll throw that out to all three of you.
Who wants to go first? Should I go? I think it's enormously important. And I think one of the things that we've seen with our audience of astronomy enthusiasts around the world is during this bizarre 2020 year of COVID-19, we've seen a major uptick in people enjoying the night sky again. The problem is that light pollution is so vastly worse than it was even 10 or 20 or 30 or 40 years ago. It's much harder for most people to see a good sky, something that everyone a century ago essentially had.
Yeah, pretty interesting to think what would have happened if this planet, instead of having some blue sky and some cloudy sky, supposing the whole planet had been covered with cloud all the time, how different our evolution would have been, because we wouldn't have known anything outside that layer of cloud. How strangely there would be no shepherds watching their flocks at night and looking up at the night sky and giving us constellations and giving us some idea that we might have some kind of place in the universe. You know, I don't know if the word universe would have existed until much later. There would have just been the Earth. Of course, we know the Earth's flat, you know, so there's the layer. Anyway, I'll stop there.
Well, personally, I see it's very important. For me personally, it's kind of moved my horizon a lot of further. It's like open up my mind. And when I go to the conferences, I have been talking in many conferences and seen all the astrophotographers there from different countries and so on. So that group knows where we are. We are under the thin foil. Yeah, the atmosphere is like a thin foil around the orange. So they know what kind of boat we are. So there's never any arguments about politics or religion or any cultural things, because those people know where we are. It's like join us together, weld us together. So I think night sky is for everyone and should be for everyone. It makes life better.
Absolutely. And JP, if any of the audience wanted to get into astrophotography like you have, what advice would you give people? What do you need to buy to be able to do it? Not that we can all create pictures like you, but if we did want to take up astrophotography, how do you start?
Well, this is less about tools. It's more about knowing what you do. And the normal digital camera, what you have today, they are extremely good. You have a nice tripod and a good digital camera and short focal optics, and you aim it to the Milky Way and take like 10, 20-second exposures and learn how to calibrate them and stack them, and you have a most beautiful pictures like NASA has published, pictures like that. You don't need much. You just need to learn and stay up all night, of course.
So a question from Live Forever today is what other space objects would you like to explore in 3D? So, well, this can be the preview for the next book, but do any of you have another celestial candidate for your next 3D explorations?
Well, for a long time, I'll take this if you don't mind. We've been looking at making a book about the solar system, really. And the solar system is all accessible to us now. The probes go everywhere. Mars, Venus, Jupiter, Saturn, Uranus, Neptune, Pluto, all the comets, all the moons of all the planets. Most of them we have images which can be in some way made to yield a stereo picture. So I've been collecting those for a long time, and I have a wonderful collaborator in Claudia Manzoni. And we've been amassing a lovely collection of all the rocks in the solar system. And at some point, we'd love to put a book out about that. That's been on the table for a while. It's just hard to actually organize and get to it. You have all these pipe dreams about books, and actually making them come to fruition is quite hard. I mean, it's a big thrill for me to see this book finally out there, because it takes a long time. And the difference between having a book nearly ready to publish and having a book ready to publish is a lot. So all credit to JP and David for getting this together. Also Robin, our wonderful director of operations in the London Stereoscopic Company.
I do have a dream. I think I mentioned it to Brian about many years ago, to have 3D pictures of northern lights. I live in 65 degrees north, so very near the polar circle. So we have northern lights. as a deep sky photographer, they are mostly like a light pollution to me, but they are really beautiful. And I think nobody ever has done that, taking 3D pictures out of northern lights, and you can do it on Earth. And I wanted to make not only pictures, but live, like movie or video film in a high resolution one, how they move water structure in 3D, because you can't see they are like flat, like nebulae, but they are close. They are like 100 kilometers from Earth.
Yeah, they're very high, so you need quite a big baseline. I've actually tried this in a very amateurish way many years ago with my friend Jamie, and we were about a mile apart. But there's two problems. Firstly, a mile isn't big enough because they're like 50 or 100 miles high, these wonderful kind of sculptures in the sky. But also, it has to be truly instantaneous because they move very fast, don't they? In real time, they're twinkling and flashing about. I have seen a very nice attempt on the internet somewhere. I have to look it out. Somebody actually did pull this off, definitely to a certain extent. A lovely dream to do, though. I'll make a whole film about this, or a book.
Yeah.
It sounds like we've got at least two great ideas for books there. Speaking of another dream, Brian, Alexandra would like to know when Queen are going to perform on the space station.
I don't know when we're going to perform full stop. I have to say, there was a plan to do a big concert on the moon, but they said there's no atmosphere.
Oh.
So I shall check out at this point. Well, I mean, seriously, it's very difficult. Our big tour of the world was cancelled when this COVID kind of cloud descended upon us, which is really sad. We had a wonderful tour sold out of Europe and some great gigs in London. So it's all put in the icebox, if you like, and we've rebooked everything for May next year. But who knows if we'll be able to do it? I don't know if the O2 can be packed with 15,000 people even in next May. We'll see. I really hope so. I would love to get on that stage and do what we do again. Fingers crossed.
And if not, it may be the ISS. Maybe that's more feasible at the moment. But hopefully we will see.
Or I'll become an astronomer.
And Brian, but actually, talking about becoming an astronomer, of course, you are an astronomer. So and Jurassic Anna would like to know, what was the one thing that did spark your interest in space originally?
I got to say, Patrick Moore had a big part of it, and I'm sad that he's not around anymore for us to enjoy his wonderful presentation. He had so much life in him. He had so much passion and enthusiasm. It was infectious. And when he talked about the Orion Nebula, we can see it in our own backyards, And I used to watch the program. I used to beg to be allowed to stay up for 10 o'clock. This is about when I was 9 or 10 years old. Please, can I stay up to 10 o'clock and see Patrick on the sky at night? And then I would go out into my garden and look up at the sky. And as David says, in those days, you could see the sky. I could see thousands of stars. These days, I go out in London, I can hardly see the plough. It's very sad. We've been robbed of our heritage of clear skies, night skies, that we can see the universe. It's really sad.
And David, what was your inspiration in astronomy, apart from not wanting to exactly do your father's career?
Simply going to a star party. And the first time I saw Saturn in a little 6-inch Dynoscope reflector, I was stunned. You could walk outside of a house in a suburban area, look into a little tube and see a planet with incredible orange color, the gap between the rings. I was stunned. I was floored. I knew I was instantly attracted to this, and I had to do something with this. So I started writing, and I didn't know what the hell I was doing, but eventually it led to this publication and brought me to the magazine.
Yeah, I'm the same. Saturn is a riveting thing. You can see Saturn right now, of course. It's quite well placed. So if you've got, even in a good pair of binoculars or a little telescope, go out a couple of hours after the sun sets and you'll see Saturn and Jupiter rising. You'll soon figure out which one they are. And it's a stunning experience just to see this tiny little object in the middle of your screen and think that is a planet, and that planet has rings around it, that planet has moons around it. Suddenly the world, the universe, the solar system is opening up to you.
That's right. And if you have 7 by 50, 10 by 50, but if you hold your binoculars very, very steadily, you can see, as you said, the little moons of Jupiter in a line. You can see that Saturn is oblong with its ring. You can repeat the observations that Galileo made that were the first telescopic observations in the history of the world with a pair of binoculars.
And this stuff you can see, even though the skies are polluted. You might not be able to see many stars, but if you go on your roof in London, as I do, you will see Jupiter and Saturn if there's no clouds around. It's a stunning thing. I recommend it.
Well, Saturn was my first too.
Really?
So we have a common lover. Actually, I bought a small telescope to my wife a long time ago, and we went together. And first time I saw Saturn, I realized that tiny dot really has a ring around, and it was so amazing. It looks 3D, and it's just floating there, and I was so amazed. And I have an art background, so I want to take a picture of it. It turned out to be a little bit more complicated than I thought, and I'm still learning it.
But yeah, no, and I think it definitely I think the first time you see Saturn through a telescope, it's just such a treat. It really is just such a phenomenal experience. But as you said, these you can still just about see in cities. We've got a question from Maria Smart wondering, where's the best place in the world to see the stars clearly? Because obviously in a lot of the cities that we're living in, you can barely see them at all.
Well, not in a city, that's for sure. Not in any city. There's a few great places. There's a couple in London. I know Dartmoor is not too bad. I know a very good friend of mine has an observatory there, and it's surprising how good that is. You've got to look at the map for light pollution and choose a black piece. But if you really want to go for it, I suppose if you go down to the desert in Chile, or in the middle of the Sahara Desert, you will get black skies, truly black skies. And there are some observatories that take advantage of that fact.
But even with the best sky viewing possible, can we observe the universe? Is there a way we can observe the whole universe? Or is there a limit to what we can actually see?
Well, I shouldn't be going first on this. David should be going, but I'm going to say something anyway. It's very tempting to kind of draw conclusions, but actually, how do you define universe? If you mean the observable universe, yes, we can see it by definition. We can observe the observable universe. If you mean the universe, we have no idea how big it is. Absolutely no idea. We can only look as far as a kind of globular shape, a certain distance from us. It's about 13.8 billion light years, right, David? Beyond that, who knows what is out there? So it's a mistake that's very often made. We should really be talking about the observable universe, because that's all we know, and that's probably all we will ever know.
That's right, by the limits of science, and the observable universe we know has something on the order of 100 billion galaxies. Back in time, telescopes are time machines. Back in the early days, there were a couple trillion galaxies. They combined into a larger number. But as Brian says, the observable universe is the limit of what we can see. And if people can look this up if they want to, the concept of cosmic inflation that Alan Guth and Andre Linde and others in the 1970s devised in cosmology means that the observable universe may not be the whole universe. And in fact, the universe may be infinite, which sounds like science fiction, but it ain't.
And if it's infinite, there's another David Eicher somewhere for sure. Right?
Oh, God,
can you imagine that?
God help them then. I thought that maybe one was too many.
I feel the same about me.
Never. So in that, and Brian, this is something you mentioned earlier on about if we'd grown up in a cloudy universe.
Cloudy skies.
Do you think we're losing our connection to the night sky? Because obviously, historically, and there are many objects in the Science Museum that show this, you depended on the sky to tell the time and to find your way. We no longer need to do that. And for many of us, I think we just don't notice the stars at all. We don't think about the night sky. So do you think we are losing our connection?
I think we do. I think we fool ourselves that we're connected because we see it on our computer screens, or we see it on the TV, or we go to movies. We don't actually see it for real with our own eyes. And I think we're the poorer for it. I think it changes something inside you. And we've all talked about that moment of looking at Saturn for the first time. It wasn't that we saw it in a book or on a screen. We saw it for real with our own eyes, and we connected. We felt something in our bodies that connected to that. I think we are in danger of losing that.
I agree. as I told before, it's for me personally, it's like moving the horizon further. So it has a direct effect how I think, and I hope more people has same possibility to open their mind. And because if you don't see the sky, you get limited, and you see inside. You are looking inside and see more details, and that cause more problems between people and stuff. But if you are able to see outside, it opens up your mind and moves your horizon away or further away. So it gives you space, pun intended, and it has direct effect to how you think. I have seen that.
There's a real, I agree so much, JP, and this is actually making me feel very emotional, because there's been times when I felt I lost my center and I lost my spirituality. And the only way I could find it really was in the stars again. I had this thing about, look at the brave stars, they were there before we came along. They'll be there long after we've all gone. There is some kind of peace up there, and all the problems that you have, and when you get depressed, when you get despondent, you look up to the stars and you feel something. There's no doubt about it. You feel connected to the universe, and you feel there is something bigger than you, bigger than your life and your problems. And it's very inspiring. I think we need to look up to the skies to find ourselves.
Thank you, Brian. I'm going to end on that note, because I think that's just a really fitting way to end this evening's event. For those of you who aren't immediately out looking at the stars, again, I will remind you that you can buy the book in the Science Museum shop, complete with glasses for the 3D effect. So if you can't immediately get out to look at the stars, you will have as good as the real thing with nebulae with this book. But of course, obviously, from what we've said tonight, if you can, and JP has told us how we can, maybe, you don't need really spectacular kit to go and get involved in stargazing. So I do suggest we go and do it. If this has whetted your appetite for more space from the Science Museum, again, just to remind you, our museums are open. We'd love to see you back in our space gallery and in our other museums around the country. We've also got lots more events coming up online. So our next big online event is Tim Peake in conversation with Susie Imber. That's on October the 15th. For more details and tickets, you can visit Penguin Live for information. But I'd like to finish tonight by thanking our three special guests for this evening: Brian May, David Eicher, and J.P Metsävainio. Congratulations on the book. It really is a tour de force. And don't forget, you can get your own copy of the book signed by Brian by clicking in the link to go to the Science Museum store. So
and by David, I have to say, and hopefully by JP as well.
It's a bonus, signed by all three, even better. So thank you for that. Thank you, all three of you. That was an absolutely inspirational evening. Thank you all for following us, and good night.
God bless.
Thank you.
Leave.